Hi, good afternoon, everyone, and welcome to our Insight60's webinar. This is a fantastic webinar we have lined up for you today. I'm very excited about it. My name is Stephen Shield, and I'm the External Relations Director here at the OGTC. So I'll be your host and compere. So we're delighted to say that we have almost about 190 participants signed up to join us today. So we'll see how many actually log on. Let's talk about a little bit about Insight60, just to give you a little bit of context. So the whole point about this series is it's 60 minutes of insightful and interactive conversation focusing on the energy transition and the technologies that drive transition. We've invited some fantastic leaders to join us and industry experts to join us. And we're going to outline the challenges and many of the solutions that are emerging to help guide us through the energy transition in this series. So today there'll be 30 minutes of, well, roughly 30 to maybe 35 minutes of insights from our keynote speaker. Then I will ask our panel to join us, and I'm very glad to say today we have a great panel. We have Gillian White and Luca Carradi, two of our leaders from OGTC, and Alan Mortimer from Wood will be joining us on the panel as well. So once the panel have kicked off the discussion, I'm sure they'll have lots of questions and insights to respond to the presentation. Then the forum is over to the participants, over to you for 20 or so minutes to steer the conversation, to ask the questions that you want to ask. You know, you can ask them directly to the speaker, or you can, type them up and I'll ask them for you. But we're always happiest to have people ask direct questions themselves. Remember, the session is designed to be very interactive, so let's use the opportunity and come forward with your questions for Suzanne. So can we move on to the housekeeping slide, please, Suzie? So we can all read. These are the rules. Please make sure that you follow them. Before we hear from Suzie, there are a few points that I just want to make just to reinforce the rules. All of you will be automatically muted and your cameras are not turned on. If you want to ask questions, please use the chat function. Very important. It's not the Q&A, it's the chat function. And I would encourage you to submit your questions as the presentation is going on. Get ready for your 20 minutes Q&A round. I'll make sure that you're called, the presentations are presented to the panel and to Suzie. We are also recording the session today, so if you're not comfortable with that for any reason, you're welcome not to stay. But we will be posting this session on our website after today. So please do stay around. Okay, I don't think that the topic for today will need much in the way of introduction. I think carbon capture and storage has gone from something quite niche and esoteric a topic to something that's actually quite front of mind now. Politicians talk about it all the time, engineers talk about it, environmentalists talk about it. I mean, it's now mainstream in terms of topical interest. A lot of discussion around it is misleading, a lot of it is possibly ill-informed. And I'm delighted that we have Suzanne Ferguson joining us today from Wood, who's an expert in the subject, to give us her insight into carbon capture and storage, where it's being used, what technologies are involved, what technology innovations are required, the ins and the outs of CCS. So, Suzie, I hope you're ready to go. Are you okay?
I'm good, thank you.
Okay, grand. I'm going to hand over to you. I know you're going to introduce yourself properly during the course of the presentation. So please do start. Your 30-minute begins now.
Thank you, Stephen, and thank you for the invitation to present today. And good afternoon, everyone, and thank you for tuning in to this presentation. So I'm often asked, particularly by friends, and friends in the environmental areas, what is the point of CCS? Because we've got loads of really exciting technologies like renewables and electric vehicles that are coming on. Do we still really need CCS? And really, what's the point? So I've prepared this presentation to try and help tackle some of those questions, and do feel free to ask whatever challenging questions you want to ask later on. So we've talked about it already without necessarily explaining the acronym. So carbon capture and storage, by definition, means capture of carbon dioxide that would have been emitted to the atmosphere, transporting it to a suitable location and permanently storing it. It's really crucial, this permanent storage, otherwise it's not going to help us to mitigate climate change for very long. Carbon capture utilization is a term that's used where we take that same CO2 stream that would have been emitted to the atmosphere, and instead we use it to create a saleable product. Now, for the purposes of abating climate change, that product needs to make sure that CO2 never gets back into the atmosphere. So some carbon capture and utilization technologies will absolutely do that, and some of them make a product that means the CO2 will go back into the atmosphere at some point. So it's worth bearing that in mind when you're looking at utilization technologies. The two different acronyms are often combined together to make CCUS. And we'll often see the UK government talking about CCUS in particular. So today I'm going to give a very short introduction. Then I'm going to talk about the various different CCS or core CCS principal technologies, where CCS can be applied to help us to abate emissions. And then I'm going to look at where it might be needed in the sort of global context of where emissions are and where they need to get to. So very briefly, I work for Wood, which is a company that was created when Wood Group and AMEC Foster Wheeler joined together 2 or 3 years ago now. Between us, we've got 160 years of history. We've got 45,000 employees all around the world and more than 400 different offices. And we are in diverse sectors all the way from upstream oil and gas down to pharmaceuticals and renewable power. And we've got people who work at the very front end of design projects, conceptual design such as myself, through to people that deliver projects and then do permitting support and even remediation at the end of life of projects. We've done a vast number of carbon capture projects. In the consulting group, we've done more than 130 different studies over the last 30 years, some of them really at the early days of looking at carbon capture technologies. We've very recently been working on the Net Zero Teesside project, which was conceptual development and pre-feed for a 700 megawatt combined cycle gas turbine with 95% carbon capture on Teesside. We've done projects that have looked at capturing CO2 from 1.1 gigawatt power stations. And we're just now finishing work on the Humber Zero project, which is a pre-feed for a low carbon industrial cluster on Humberside that would see 7 million tons of CO2 captured. We've also got a long history in hydrogen. We're a licensor of a hydrogen technology, and we're pioneering a blue hydrogen technology and a biohydrogen technology. And we also have groups that work in wind and solar and are leaders in these areas. But since we're a people-based organization, I've just got one slide on me. My generation, I'm just about young enough to remember learning about the Rio Accord in school and then seeing the Kyoto Protocol as current news when I was a teenager. So I found this really exciting because a lot of nature programs around the time were all very depressing about how things were all being destroyed and isn't it terrible what mankind has done to the earth. So seeing these things, these big global changes come in, made me really thrilled, and I decided to study chemical engineering as a route to try and help these new technologies that could tackle climate change to come about. I joined the oil and gas industry when I graduated, and I was able to move into CCS in 2006 when I first discovered what it was. And I thought, that sounds a brilliant idea. Let's take the CO2 and put it underground instead of sticking it into the atmosphere. So I've been involved in studies and projects in this area for most of the last 13 years, which also makes me a veteran of some of the UK government's brilliantly cancelled projects. So what are the main technologies that are involved in capturing carbon dioxide? The most commonly used technology that features in a number of existing projects around the world is called pre-combustion CO2 capture. This literally means capturing the CO2 before any combustion has taken place, but that means it also covers CO2 capture from streams such as natural gas or from the syngas part of hydrogen production. It doesn't necessarily mean that downstream there is some combustion. So when you're capturing CO2 from these streams, it's at high partial pressure and there's no oxygen present. And most of the existing CO2 capture units that use this technology vent an almost pure CO2 stream directly to the atmosphere. If you want to use a pre-combustion CO2 route to power, then you're taking a fuel and removing all of the carbon content from that fuel, and then combusting only the hydrogen components. And if you're using that from coal or natural gas via gasification or reformation, you've got this lovely, rather complicated flow scheme for a power generation system. And it'd be wrong of me not to mention Schleipner's project, which has been capturing 1 million tons of CO2 since 1996, for anyone who needs a handy reference point if they're challenged about CCS not working and none of them existing. This project has been operating very smoothly for all of that time, and it captures the CO2 that exists in the natural gas reservoir that has to be removed before the natural gas can be sent to land to be used in the national grid. And our colleagues in Equinor say that this project is really rather boring because it just works nicely. Post-combustion capture is literally capture of CO2 after the combustion has taken place. So you're combusting any hydrocarbon containing feedstock, and then you're capturing CO2 out of its exhaust. The most proven technologies in this area are solvent-based ones, and the highest efficiency ones are proprietary-based solvents that are operated by large companies that have got quite a good, useful track record in delivering big projects. One of the challenges is that because exhaust gases are at near atmospheric pressure and they can contain only a small amount of CO2, maybe as little as 3.5%, the equipment to capture CO2 from this large volume, low pressure stream is very large. So you can see in the picture here, this is a picture of Sask Power's power station at Boundary Dam in Canada. And at the very far right of the picture, you can see the CO2 absorption tower at this power station. Now, this is a huge tower, but you can see it doesn't look ridiculous next to the power station that it's next to. So this has been in use for a number of years. This plant's been operating since 2014 in Canada. There is also oxy-combustion CO2 capture. So usually people will talk about these three separate technologies for CO2 capture. This means literally combusting with oxygen instead of air. So post-combustion capture, a lot of the work done is removing the nitrogen, separating CO2 from a stream that contains mostly nitrogen. If you combust with air, with oxygen instead of air, then the nitrogen has already been removed, and you end up with an exhaust gas that comprises mostly CO2 and water, which is much easier to separate. However, that does mean that you need an air separation unit to be able to remove the nitrogen upstream. There's some really exciting technologies in this area. The picture on the left is Net Power's alum cycle plant, which is in commissioning and demonstration in Texas, which could be a real game changer for low carbon power generation. And the one on the right is a picture of the Compostilla project, which is in Spain, which has a retrofit style design to an existing design of a circulating fluid bed boiler. So if you want to add oxy-combustion to something, you need a flue gas recycle to help moderate the temperature. And of course, you need an oxygen supply. This could also be a promising technological option for decarbonizing FCC units, where there aren't really very many choices. So that's a very brief crash course in what the different technologies are. So what can we do with them, and how does that help us? Pre-combustion technologies are already used very widely around the world. They're used in gas treating plants, LNG liquefaction plants, and so on. And they produce a CO2 stream, or that is usually vented to atmosphere. This means that in order to add CO2 capture to this scheme, all you really need to do is to connect up to divert from that vent, add a compressor, and then connect to a storage site. which, if you have a portfolio of different assets, is often the lowest cost route to reducing emissions from any particular sites. So particularly looking at gas treating plants, if you've got an existing gas treating plant and you're venting some CO2, you're near a location where you might be able to store it. It's a real win-win situation as a first project to go for. But pre-combustion capture can also provide a route to decarbonising fuel gas systems on big integrated plants like oil refineries and steel plants. This is by generation of hydrogen, either through a gasification route or reformation, removing the carbon dioxide and capturing it, and then using the hydrogen as the fuel stream. This can also be used on a much grander scale to decarbonise domestic gas grids, and I'm sure people will have seen a lot about this in the news. A good example of a pre-combustion capture project is the world's largest CO2 injection project. This is in Australia on Gorgon's LNG plant. Now, this is an interesting case study because this project would not have received the permit to operate if it had not agreed to put CO2 capture on the plant. So we can talk about the cost and whether or not we need it, but at some point we also need to talk about whether or not plants should be allowed to operate without CCS as well. So this project has been running at full scale now for a few months. Our team up in Aberdeen helped to get the injection working nice and smoothly. So uses of post-combustion capture, it is of course already used. We saw the example of the power station in Canada, but it's also been used at both coal power plants and fertilizer plants for several decades as a method of obtaining CO2 that's then used as a chemical feedstock. So it's a process that's been in use for a long time. What's really handy about it is that it's a bolt-on-the-back solution, so it doesn't interfere with the chemistry and it doesn't require a significant rebuild of any sites. So you can capture greater than 95% of the CO2 in any exhaust gas. Now, of course, really dirty exhaust gases with lots of NOx and SOx and particulates in them require more upstream treatment, but those streams quite often have a higher concentration of CO2 than some. So all in all, it's still very doable to do CO2 capture from these streams. It's good for capturing CO2 from baseload or grid-responsive power plants, combined heat and power units, industrial-fired heaters, and places where you've got unavoidable chemistry involved in CO2 emissions, like a refinery FCC unit. It can also be used on cement and lime production flue gases. Now, cement and lime results in around 8% of all global emissions. When this is not fossil-derived, or not fossil fuel-derived CO2 emissions, but it is CO2 that's come out of the ground. This is CO2 that's been driven off limestone in order to make lime as part of the cement making process. So it's really important that we can capture that CO2 and put it back in the ground instead of letting it go into the atmosphere. The example project I've got on the screen here is a pretty picture of a glass float line. This is at NSG's plant in St Helens in the northwest of the UK. This is a challenging plant because it's one of those sites with high NOx and SOx and particulates emissions in the flue gas if you take the flue gas upstream as their pollution control unit. But we got some really excellent information from a number of different licensors who were very excited at the opportunity of bidding to put a carbon capture unit on this site. And I've got a nice picture of Acker's very smart looking Just Catch technology, which they have been working very hard to refine their containerized small scale design for carbon capture units for applications just like this one. Another application which isn't specific to certain capture technology is the use of CCS for greenhouse gas removals. Now, it looks very likely that we're going to need some form of greenhouse gas removal technologies in the system to get to net zero. So looking at CO2 applied to bio-derived CO2 streams has got the potential to result in negative CO2 emissions. One option is to capture CO2 directly from the air, where it is 400 parts per million, very low concentration. These technologies exist and they're running smoothly, but they're using energy and the only product is to capture CO2. Other ways to capture CO2 and reduce its concentration in the atmosphere involve using trees to capture that CO2 or any other form of biomass that grows. This can be put into bioenergy with CCS plants. So I'm sure you will all have heard of the Drax Bioenergy with CCS project. If not, the concept is on this lovely animation they have on their website, which shows CO2 from the atmosphere being absorbed by trees. The trees are then used in the timber industry, mostly in the US, and it's wastes from those timber industries that are formed into pellets, shipped across from the US timber industry, shipped to Drax, where they are combusted to make a huge amount of the UK's power. I think I checked just before this seminar, and we had about 2 gigawatts of power in the UK coming from bioenergy. Now, if you take that exhaust stream from Drax and you were to capture the CO2 from that exhaust stream, you're effectively capturing CO2 that was in the air, albeit in the United States. So if you capture that CO2 and you store it geologically, then you've had a net removal of CO2 from the atmosphere. But there's plenty of other biomass and biogenic CO2 streams you can capture. There's also biomass routes to hydrogen, either through gasification of biomass or bio-derived wastes, or reformation of biofuels, if you can find sustainable biofuels to reform. You can also capture CO2 from energy from waste plants or waste to synfuels process, like the Velocys process, where they're taking waste and they're using it to make sustainable aviation fuel. They also produce a CO2 stream, and that CO2 can be captured. And depending on the biogenic content of the original waste stream, which is often more than 50%, there's potential there for those streams to be net negative as well, whilst they're producing useful products. And then, of course, there's a number of biogenic CO2 streams that are almost pure vented into the atmosphere at the moment, like the off-gas from brewing and other fermentation processes like making vinegar, bioethanol production, and the production of biomethane. Capturing CO2 from those streams would also be net negative. It wouldn't be 100% net negative, of course, because you need to account for the energy that's used, but there will certainly be some negative proportion. So what does that matter in the overall context when we're trying to get to net zero around the world? Well, this is the IPCC's 1.5 degrees report, which is probably the most fundamental report governing this area to date. And most importantly, it says we can limit global warming to 1.5 degrees, but it requires deep emissions reductions and rapid, far-reaching and unprecedented changes in all aspects of our society. Now, we've demonstrated this year through horrific and tragic events that we can make unprecedented changes to our society when we need to. So hopefully that gives us some degree of confidence that we will be able to make the changes needed to also tackle the climate crisis. So this report stated clearly we must reach net zero by 2050, but perhaps an even more challenging target is that we also need to reduce our net emissions versus 1990 levels by 45% by 2030. That's less than 10 years, and we've lost one of those years to COVID. So we've got a huge amount of work to do, bearing in mind that it takes 5 years to build a project. That's a massive challenge that we really need to get moving on right away. So globally, these emissions come from a wide range of sectors. We all know about electricity and heat and how burning coal and oil for heat and power is a major source of CO2 emissions. We also burn fuels in industry, but we also have chemical CO2 emissions, so such as the emissions from the cement industry, which are unavoidable if we want to have cement. There are also significant emissions from agriculture and, of course, from transportation. Not just the cars we see on the road every day, but haulage fleets and also marine, parts of the world where the ferries are a very significant amount of their carbon footprint. And of course, we use it in buildings for space heating, water heating and cooking, or we emit CO2 through these processes. Looking at the world is pretty daunting. So sometimes it's a bit easier to think of it from a UK emissions sector, by sector. So in 2018, we emitted more than 450 gigatons of CO2 equivalent. I've got a G missing from my slide, I do apologise. And we can see from this nice grid that BEIs have produced where our emissions mostly come from, the largest sector now being transport. In the UK, we've done a great job of reducing the carbon footprint of the country as a whole, mostly by dramatically reducing the carbon footprint of our electricity supply. And we've done this by turning off coal, building lots of renewables, which is great, but also by building and continuing to run a lot of natural gas plants. Natural gas plants that are unabated still usually make up the largest proportion of our electricity. So we've got a long way to go in the energy sector still. But even if we get the energy sector to zero, we still have all those other sectors on the grid to deal with, which are a bit more difficult than just putting a restriction on the few very large energy suppliers. The picture on the right is a picture of the UK's emissions that are anticipated through current law in the UK. And you can see that we've done a great job of reducing our emissions, but we're absolutely nowhere near net zero, nor are we really very close to a 45% reduction by 2030. And this shows that we do need major changes to UK law if we're going to get to net zero. But luckily, BEIs are working on this, and people like the Department for Transport as well. So hopefully we will see those major changes. But what we can expect is definitely there must be changes. But what's this got to do with carbon capture and storage? Well, really, my point here is that electrification will help us to decarbonize a huge number of these sectors. So we have great progress in electric vehicles. We've got heat pumps increasing uptake, which will help with residential heating. But these things are quite expensive. And if everybody does them, we're going to have to dramatically increase the size of our electricity grid, which is doable. But that doesn't help us to tackle emissions from agriculture, and it doesn't help us to tackle emissions from the cement and steel industry. So we can decarbonize a lot of things with electrification and our wonderful nuclear or renewable power, but it can't tackle all of our emission sources. We need some other options. So if we want to continue to have steel, cement, lime, and glass, all of which emit CO2 as part of their raw chemistry, because they have something like limestone in their ingredients, and CO2 is emitted to make their products, we can capture that CO2 and store it geologically to make sure it doesn't go into the atmosphere. There's also not a currently available way to reach net zero from agriculture. We can reduce emissions for agriculture, to be sure, and certainly some of the agricultural emissions relate to vehicles, which can be either electrified or changed to hydrogen. But fundamentally, if we still have ruminants and rice paddies, we're still going to have naturally emitted methane emissions to the environment. And even if everyone goes vegan, we probably still want wool, and sheep also emit quite a lot of methane. So we'll need to balance that by geologically storing some CO2 that's been captured from the biosphere elsewhere, or using direct air capture to take it out of the air. And even using direct air capture means you have to have a carbon capture and storage system to take that CO2 and store it forever so that it doesn't get back into the atmosphere. And if you've had to have a carbon capture and storage network system so that you can take those emissions that you can't avoid or can't prevent going into the atmosphere via any other means, then having that system means that you also have all these other choices of ways of abating your emissions. So you can use CCS to reduce emissions from existing fossil fuel power stations. A project could be built in 5 years or less from today to reduce emissions from our existing power stations by more than 90%. You can apply CCS to natural gas for large-scale hydrogen production, and that can be used to decarbonize domestic heating and vehicles at a much greater scale and a lot sooner than if we were to purely rely on using renewable power to electrolyze water to make that hydrogen. Then you can use CCS processes to capture CO2 directly from the air, that we've talked about. So it's an option, and it may be a last resort, but it exists and it works. And then, of course, we can use CCS for biogenic CO2 streams to generate carbon negative electricity or other carbon negative streams. So having CCS gives us many more routes and options to decarbonize, so we can find the most effective, the most logistically simple route, and the lowest cost route to decarbonize each individual part of our society. And above all else, it gives us the ability to achieve net zero. The Committee on Climate Change has said very clearly that none of their models can converge with net zero achieved without at least some level of CCS in the system. So thank you very much. I think I may have rattled through a bit. I hope I was understandable. And there we are. Thank you. I'll pass back to Stephen.
No, that's great. Thanks so much, Suzie. That was fantastic. A great overview of some of the key projects that are already up and running and out there, and some of the technologies involved. I'm sure our panel will have tons of questions to pose to you, and this is the stage where I'm going to bring them into into play. Let me ask them to introduce themselves. We have Gillian White. Gillian, can you tell us who you are, where you're from, etc.?
Yeah, afternoon, everybody. Great to be here. I'm the Solution Centre Manager at the OGTC for subsurface and also wells. My background is geoscience, everything to do with the reservoir and the subsurface.
Super, thanks. And Luca, please introduce yourself.
Hello, everybody. I'm Luca Corradi, the Innovation Network Director here at the Oil and Gas Technology Center.
And last but no means least, we have Alan Mortimer from Wood. Alan, would you like to just say a few words about yourself?
Hi, good afternoon. Alan Mortimer, Director of Innovation for Renewables for Wood.
Thank you very much. So, panel, you've sat through the presentation. I'm sure there are a few points that you would like to put to Suzie, so please fire away. I think I'm going to come to Gillian first. Gillian, what would you like to comment on or ask of Suzie?
Yeah, thanks, Stephen. So I guess my first comment is, well, there's an awful lot going on already in CCS. Great overview, thank you very much. My question actually, Suzie, is to do with innovation and future innovation. Could you maybe name a couple of areas where you think you can see that we can really benefit from some rapid innovation to get CCS developed even more quickly?
Yeah, good question. Thanks, Gillian. I think one of the things that really has people worried is those residual emissions from CCS. So if you have, say, a hydrogen production unit, it can capture 95% of the CO2 that is produced through the production of hydrogen. But what about that remaining 5%? And I think going after those last few percentage points, or optimizing that and determining, well, actually, maybe it makes more sense to have 5% of biofeedstocks in the fuel than being able to go after that last 5%. It's going to be really important. So tackling the residual emissions from CCS, but also from making sure that we've absolutely minimized the environmental impact of any of the CCS technologies. So some people are concerned about any emissions of, for example, some of those solvents that are used to the atmosphere. Now, the technology providers have been working very hard to make sure that they're at very, very low levels. And they're certainly extremely competitive with a lot of the technologies that we've got already around the country, in the UK or around the world, where our other industrial emission sources are far, far more significant environmental impact. But I think making sure that people are absolutely confident that we've minimized the environmental impact and it's not going to have any other, unforeseen side effects of doing CCS is going to be really important.
Thank you.
Thanks, Gillian. Alan, you're obviously a colleague of Suzie's. I'm going to give you the opportunity to come in and make any observations at this point.
I am a colleague on the renewables side, but thanks, Suzie. I mean, that was a great insight there. And if I can be parochial for a minute, it does look like the UK can be a leader in CCS, and CCS will have a big role to play globally. What do you think we should do to fully maximise the jobs and economic benefit for the UK?
I think that's a really good question. And I think that's something that the UK could have done better with the rollout of our renewables technology. I've certainly seen people complain that not enough of the supply chain is from within the UK, and that's perhaps something that we've missed. I know that BEIS are looking at this and they're very keen to understand what they should do, but I think it's going to be crucial to make sure that we not only demonstrate CCS in the UK, but that we're making sure that the learning from those demonstration projects is really assimilated within the UK engineering base that we have. We've got so much expertise in the oil and gas sector, and it's really not very different to then apply that expertise to moving CO2 around and to moving hydrogen around compared to moving other high energy density liquids around. That really we can really make a good play of transitioning the expertise that we have to decarbonisation projects instead. And then making sure that UK companies are really well involved in supplying the technologies as well, and getting community involvement whenever possible. So a lot of these projects are going to be in areas, hopefully, in areas which have seen some decline recently. So places where they've seen a huge number of job cuts because of industry closures. For example, like the Teesside project, the Teesside Net Zero clean gas project, where we're looking at building this combined cycle gas turbine plant, is on the actual site of the Redcar Steelworks that's been shut down. And it was famously reported in the media that those people who'd done their steelworks apprenticeships should now go and work in Costa, I think was the quote. So we can give them, by building these projects, we can give them something that's hopefully a little bit more challenging and interesting for them to do.
Well, I quite like coffee myself. I'm sure there might be one or two people who have worked in Costa who will take that up with you, Suzie. So, Luca, please come in and ask your burning questions.
Well, just a comment first, if I may, because I thank you for the presentation, very informative. And I agree there's the advantage in the UK for the capital of skills and experience in the oil and gas industry that can be applied, and therefore there's an opportunity for the UK. But that is also uniquely combined with the availability of storage location in the UK continental shelf. Because when you look at the carbon footprint of Europe as a whole and how much CO2 will need to be captured across Europe, then the UK continental shelf and the Norwegian continental shelf are most likely the places to go. So there's an opportunity there to make a big advantage for the UK in addition to tackling the challenge of carbon capture for climate change. And on that, that's my question, if I can do that, is, you mentioned the 1.5 and in a recent report by the International Energy Agency is showing that the increase in temperature, which is locked in the infrastructure. So in other words, all the power plant and industrial plants that are in operation today and are being built today, if they keep producing and working for their expected life, they are generating a 1.6 increase in average temperature only from that area, without counting agriculture and the other areas. So we have to do something about that. So the question is, do we retrofit them with carbon capture and storage at scale, or will we have to abandon them and replace them with something with lower emission or zero emissions? What's the best way from a carbon emission perspective and an economic perspective?
You're probably not going to like this answer, but I'm going to say that it depends on what the site is and what its future looks like. So for sure, there are some assets where they'll be running today and they might only have 5 or 10 more years of that asset to run. But if a legislation or a carbon tax or something comes in that means they've got a tougher choice between fitting CCS that might only run for 3 or 4 years after they've built it, then I would expect them to say, well, it's actually more economic for us to shut down in favor of another technology. But if you then look at somewhere like the huge number of really quite new, relatively high efficiency coal plants they've been building in China, then it's a really different story. So a lot of those plants, and also it's a real moral question as well. There's people who have not had access to electricity, and now we're saying they should shut down their power plants and not have electricity again. It's not really a really good solution. But I was lucky to hear one of the ministers, I think, in charge of a whole area of China and their energy industry, who said, well, we've fitted FGD to every single coal power plant in China in 10 years. So we'll do the same with CCS, which is really exciting. And we absolutely should all get into building CCS plants if that's the case.
Good.
So I did get the answer.
Thank you. Thank you, Luca. Now, you are a panel. I don't expect Suzie to field all the questions that will come from the audience, but now is the time to turn to the audience and ask them to take part. Panel members, you will be asked to answer questions as well, so please stand by. So I'm going to start the ball rolling on behalf of Joseph Nicholson, who asked the very first question in the chat room about data. What data needs to be collected to monitor and ensure permanent storage of CO2? And how transparent should this data collection, processing and analysis be to the public and environmental stakeholders to gain trust? Which I think is a very pointy and difficult question, but who would like to tackle that one? I think
I can take it.
I'll break the silence. I think it's very important, and I think the oil and gas is already collecting and sharing information about its own emission with the Oil and Gas Authority, and it will be doing even more so. So I don't see any reason why CCS should do anything less than that as a starting point, and probably more than that, because the point of reassuring the various stakeholders and the general population about the ability of a reservoir and or CCS plants to actually capture and contain and retain the CO2 without leaks is an important. I think several studies from the Center for Carbon Capture and Storage of University of Edinburgh, Stuart Hesselden, and Professor Stuart Hesselden and beyond, have shown that the likelihood of leaks from a reservoir offshore is so minimal and very minimal. But that's a language for engineers. The language for the general public should show the data, reassure that, and make it very clear. So I'm in favor of the maximum transparency we can do.
Suzie, what's your perspective on that one?
I'd absolutely agree with that. It's really important, but for several reasons, not just to reassure people that the CO2 isn't leaking somewhere beneath the seabed many kilometers away that they can't see, but also because a lot of these projects are going to be sufficiently expensive that they're going to have some sort of societal backing to achieve that carbon mitigation, which means that there's effectively taxpayers' money going into making sure that that CO2 has been stored. People are going to want to know that it actually is stored. So, and also eventually, this CO2 needs to stay in the ground for geological time, which is much longer than companies last for, which means at some stage, the liability for that CO2 storage will pass to the state of any country where there's CO2 storage. And that will then absolutely be the business of taxpayers and voters to make sure that that CO2 is fully visible, that it's well stored, and that it's being kept out of the atmosphere.
Excellent. Alan, did you have any perspectives on that one before we press on?
Just really lessons from other industries, and that openness is really vital to building public confidence, and it seems that this is an issue that the public could be concerned about. So the more open and transparent we are, the better from the start. Okay,
grand, good. Well, the next question actually builds on that whole point of whether or not we can make sure that the CO2 that we put in the ground stays in the ground. So I'd like to come to Gavin Munro. Gavin, you've got a very interesting question, which is really a subsurface question, which I'm sure Gillian would possibly jump in first to answer. Gavin, can you hear us?
Yeah, can you hear me? Yeah,
yeah, we can.
Gillian, yes, Suzanne, very much enjoyed your presentation. Excellent, really good. I'm just finished the North Sea measurement workshop, which was taking place over the last 4 days. And one of the presenters indicated that when CO2 gets injected into the reservoir and mixes with reservoir water, it can produce carbonic acid. And they had shown that some of the reservoir rocks could actually be dissolved. And it's possibly a very basic question. Does that raise a concern, or has that been addressed?
Yeah, no, it's a very good question, a very important question. And I think the answer is that, well, carbonic acid is a weak acid. It doesn't dissolve all rocks. and all minerals, it would dissolve calcium carbonate, as we alluded to there, talking about cement manufacture and so on. But the main thing, I think, is to mitigate this happening by not injecting it into rock which you think are susceptible to being dissolved, and also by really understanding the cap rock quality. Luckily enough, in many hydrocarbon basins, we've got a really good understanding of this already from the subsurface evaluation that's been carried out. But it's a key part of evaluating any site for CO2 sequestration. Absolutely, very important. And yes, it is possible, and you absolutely want to mitigate against it.
Excellent. Okay, good.
Cap rocks such as salt, of which there's plenty in the southern gas basin in particular, but also elsewhere in the North Sea. There's very low chance of being, well, it wouldn't be dissolved by carbonic acid. So that's just one example, but it is possible to mitigate.
I did think it would have been addressed, but I was just wanting to be sure.
Yeah, that's a very good question.
Thanks.
Thanks very much, Gavin. And thanks, Gillian. Very comprehensive answer. I'm going to shift gears a little bit, a different type of question, and I'm going to come to Erica Askeland, who's been asking a question about direct air capture. So, Erica, can you hear us? Are you willing to kind of jump in and ask your question, please?
Yes, I am. Thank you ever so much, Stephen. And what a great presentation. It's been really informative. I just thought it was worth asking if, I mean, knowing that clearly all of these approaches and all of these, methods of, taking CO2 out of whatever systems, there's probably all numerous silver bullets rather than just one. But I was curious when you were talking about, removing CO2 from the air already. That kind of seems like a no-brainer, except you did actually describe it as being, the last resort. So I was just wondering maybe if you could tell us a bit more about what the barriers and risks are to implementing that.
Yeah, no problem. Thank you. It's a good question. So direct air capture is basically a very clever black box that has a lot of fans on, a bit like a whole load of computer fans. And that will pass the air over an adsorbent bed where the CO2 is removed from the air, and then the air minus the CO2 that was in it goes out the other side. And then the CO2 is captured from that adsorbent, and then it can be produced as CO2 as a liquid form that can then be used. And in some cases, it's captured this way from the air, and that CO2 is then sold into the chemicals industry. So there's a very innovative company called Climeworks who have several plants around the world, and that's what one of their plants in Switzerland does. So essentially, they're using energy to take CO2 directly out of the air, and then they sell that CO2 for chemical uses. Another plant they have, which is in Iceland, that CO2 is then stored geologically, and it's part of a pilot plant that then uses some additional technologies to take that CO2 and make sure it turns directly into limestone underground, which is really clever. But their business model is basically to use power and sequester CO2 out of the air. And they do that because people pay them to offset their CO2 emissions from somewhere else. So it can work, and there is a business model that makes it work, but it's not necessarily the lowest cost or the solution to abate for example, 458 gigatons of CO2 that's emitted from the UK at the moment. But I don't think there's any particular health and safety issues with it. It works, and it's just that it's very small scale compared to the total need for CO2 sequestration at the moment, and it does consume energy in the process.
So when you say it consumes energy, Suzie, I mean, are we talking vast quantities of energy for the return that you'd be expected to get from a direct air capture plant?
Well, they obviously managed to make it balance as a business, and I don't think it's probably not $1,000 a ton of CO2, but it certainly wouldn't be. Thermodynamically, it couldn't possibly be cost competitive with capturing CO2 from, say, a natural gas treating plant where it's pure CO2 and all you have to do is add a compressor.
So it sounds like an area of innovation, perhaps, to make it more cost effective or reduce the power demand to produce the effect needed.
Yeah, and there's several good technology companies that are out there doing it and who are working on that now. And I
Excellent.
think, doesn't OGTC have one?
We do, is
Yes.
one of our pioneers in the TechX Accelerator program, and thank you for that. You can find more about them on our website.
Yeah, I was going to come to you, Luca, to ask for your perspective on direct air capture.
I think direct air capture is definitely part of the solution. It's not a silver bullet, as Suzanne said, but we are most likely, if not certainly, overshoot the carbon budget, which means the amount of CO2 we can keep putting in the air before we hit the 1.5 degrees. So we'll have to take carbon out of the atmosphere, and the direct air capture is one of the way of doing that. The problem, as Suzanne mentioned, is the cost, the current cost of doing so. So technology innovation is absolutely crucial to reduce that cost. But it's a cost which is expected to be high at the moment because it is a very, very early stages technology. There are two common. You mentioned Climeworks, the other is carbon engineering in Canada, which is using a slightly different approach. And of course, our TechX pioneer in the very early stages is about reducing the cost. It's about innovation technology to reduce the cost, while at the same time we learn how to do that thing in a more effective and efficient way.
Excellent. Good. Well, let's move on from direct capture to something completely different. Daniel Coyle, you've got a question about challenges. What are the main challenges? Would you like to pose your question directly to Suzie?
Yeah, thanks, Stephen. Hi, Suzie. Really enjoyed the presentation. I worked on a number of projects where we've looked at the sequestration of CO2 in offshore sites. You mentioned the Sleipner project earlier. But I was just wondering, through your dialogue with the industry leaders, what do they see as being the main challenges? Is it storage or transportation, or what's the difficulties that currently exist?
Hopefully everyone managed to hear that. There was a little bit of interference on the line there, Daniel. Suzie, are you happy to tackle that one?
Yes, so in case anyone didn't hear, Daniel's question was about what's the largest challenge in making CCS projects happen. And I would say that it's absolutely in the legislature and regulation to make that happen, because at the moment people can just vent their CO2 emissions and they either pay nothing or they pay such a small amount of carbon tax or carbon price that it's not worth them not emitting that CO2. And I think that's our major challenge, because absolutely you have to use some energy and you have to build some more equipment to be able to capture the CO2 even before you start talking about pipelines and change of use of oil and gas facilities from production to storage of CO2. And all of these projects cost money. And until people are paying for having emitted their CO2, they won't make money as a project, and people would be, investors won't support them. So the biggest thing we need is new business models from governments, or some sort of global carbon price. If we could imagine the world could ever agree on something globally like that, that would be brilliant. I think I saw a quotation the other day that said just 18% of all CO2 emissions in the world are subject to some kind of carbon tax or carbon levy pricing. So that will include the people who are covered by the European Emissions Trading Scheme and the emissions trading schemes in places like California. So I think that's our biggest challenge. But if you want to talk about technical challenges, then I think it's making sure that each project is developed and implemented in a way that is practical. So making sure that we have the right project for the right application is really important. And that way that's also going to be necessary to make sure that we keep the costs of each project down, but to make sure that we show that the industry is as smart as it needs to be to put the right project in the right place.
Excellent, thank you. There was an example given in the presentation about one of the projects that has CCS already installed. I'd like to ask Kevin Turner in the audience to ask about that project. I think it's Sask Power.
Yeah.
So Kevin, are you there?
Yeah, I'm here. Hi, Suzie. Excellent presentation. Thank you. Just regarding the Sask Power, that's only a province away from where we are, so it's in the news sometimes. The indications in public knowledge appear that the capture is lower than the 90%, I believe you said, targeted for post-combustion. So I'm just curious if you have any info on what the actual capture rates are. As well, secondary to that, how much power is used? Because I've heard numbers 15% type reduction in net export from a power facility. to facilitate the carbon capture.
Okay, no problem. Those numbers don't sound wildly out. So yeah, the Sask Power project was the first really large scale project that was deployed by Shell for their CANSOLV technology. And there's a certain amount of finger pointing, but I think it's always going to be a challenge with one of these first of a kind plants. They've learned a lot through demonstrating it, but initially I think they had some real problems with some of the components that were in the flue gas stream that weren't expected to be there, that were causing some problems with the solvent's ability to capture the CO2 or with its reliability. So they were troubled with not very good availability for the first couple of years running, but they then shut it down. They fixed a lot of those problems, and now it's running at a much higher availability. But don't know off the top of my head what their target design rate was for, but most projects were designed for 90% CO2 capture until quite recently, and it's only the projects in the last year or two that we've seen are starting to go for that higher CO2 capture rate, where the licensors are saying, well, we designed for 90 because you told us 90, we can easily do 95. So now we're going to, well then give us 95. So that's what we're designing for now. And in terms of the quantity of power that's reduced from a power station, it can be significant. So like it was raised by Daniel just now, you do have these challenges because it does cost energy in the form of heat for solvent regeneration for a capture project like Sask Power's, as well as for the compression of the CO2. And those are the two main parasitic loads that will be on a power plant. And they can result in emissions in power production reductions, of course. And I'd say, I can't remember off the top of my head, but I think the numbers you're quoting are around about right for one of these first of a kind projects. And we'd probably expect to get a bit better than that now. So a new build power station like a combined cycle power plant, which you would expect to be around 60% efficiency, with a new carbon capture plant that's well integrated with it, you'd be expecting to see that drop only to say 53% efficient.
Thank you.
Okay, very comprehensive response, and thanks, Kevin, for asking that question. Interesting project. Let's go from a power plant to the reservoir, going back to the reservoir, and I think this is one for Gillian. Augusto Bolte, are you happy to pose your question about wellbore pressure?
Thanks, Stephen. Yeah, despite the benefits of CO2, EOR, and CCS programs and so on, isn't there problems like if wellbore pressure goes lower than reservoir pressure, does possible blowout, and how could this be prevented? Thanks.
Yeah, good question, Augusto. I don't know the detailed answer to that, but I do know that understanding the precise operating conditions that you have in any given reservoir and any set of wells is fundamentally important to how you design your injection strategy. So the two main sort of underground types of storage facility are what's called a saline aquifer, which tends to be at sort of pressure equilibrium with the rest of the formation, and depleted reservoir, which is somewhere that you've perhaps already extracted oil or gas from. And they present different problems, and you have to combine that set of physical parameters with the understanding of the phase changes of the CO2 as you're injecting it. So it does need to be absolutely managed. It depends on the pressure of the reservoir that you're entering, and the selection of site obviously has to minimize that kind of risk happening. And I think it's entirely possible to minimize that, and also using wellbore pressure control valves and so on, just as we do in extracting hydrocarbons. The same sort of set of pressure control and so on would have to be in place, along with very careful wellbore design to ensure the integrity of the wellbore. The materials choice, the metallurgy choice, and all of these things must be taken into account very carefully. So I hope that's a sort of a short answer to your question.
Sure. Thanks.
Thanks, Gillian. We've almost run out of time, but I'd quite like to finish on a question about skills and transferable skills. And Emily Early, if you're there, I'm going to give you the last word if you're happy to take the opportunity. Nope, maybe a bit shy. Let me ask the question for Emily. So Suzie mentioned transferable skills from oil and gas that can be used for CCS. Are there any initiatives that you're aware of at the moment that enable this transition for individuals that are interested in getting involved in CCS? So a really good question to end on, Suzie, given the fact that your whole career has been centered around this question. What advice would you give?
Well, you've certainly started with your own investigations by coming to this webinar, which would be a really, really brief introduction to the area. So thank you for doing that. I think it's a really good idea to suggest that there should be some programs to help people to move from oil and gas into technologies like CCS and hydrogen generation, because they are the same fundamental skill sets. I mean, we're all, or almost all, chemical engineers, I would guess, and mechanical engineers, and it's all a lot of the same stuff that we would normally do. So we're talking about thrilling things like insulation and instrumentation control, absolutely crucial to making these projects work. But it's a really good idea, and I think maybe it's something that we could take away from today, is to talk about how we can support or help to champion the concept of having a training scheme to help people to develop skills from what they currently have in their current industry to ones that they want to go into. Actually, probably really pertinent for this point in time as well.
It's a great way to end the discussion. I have to say thank you to Suzie and all the panelists. What a fantastic presentation, Suzie. Really, really enlightening, and great questions and answers from the panel members as well. So everyone who dialed in to watch this webinar, I know we've had a lot of folks from Canada join us very early in the morning for them. So thank you for doing that. Please do feel free to kind of follow us. There's a link in the chat room that shows you how to sign up for all of our up and coming webinars and other events. Other than that, I would encourage you to join us tomorrow actually for our Tech 20 virtual, which is all about green hydrogen, and that starts at 11 o'clock tomorrow morning. You can find details about that on our website too. We've got to the end of our session. Suzie, panel members, thank you so much. Thank you participants for asking your questions, and we look forward to the next Insight 60. Thank you. Bye-bye.
Thank you.
Thank you. Bye.
Thank you.